Let's look at a specific type of reaction called a Pinacol Rearrangement. Let's look at the mechanism for it. In this case, we have a diol, a vicinal diol, two alcohols on adjacent carbons in the presence of acid, which we'll just denote as H+. First thing that's going to happen is the electronegative oxygen from the alcohol is going to go ahead and get protonated, pick up the H+. And we're going to go ahead, we'll have our methyl group, OH. Now either one of the oxygens could have gotten protonated. I protonated the one on the right over here. So now that oxygen has picked up a hydrogen, this hydrogen right here. Let me draw the methyls, methyl, and now this oxygen is going to have a formal charge of A +1. At this point, as soon as the alcohol gets protonated, this becomes a really good leaving group. Water is an excellent leaving group. So it's going to go ahead and pull these electrons, pull off and leave, and end up producing a carbocation at that carbon right there. So we have a methyl group. Now this is a carbocation. On the left we have methyl group, and this OH over here, this alcohol is still sitting there. I'm going to put brackets around this because that's you cannot isolate a carbocation, and a water molecule has come flying out. Now, at this point, every time you get a carbocation, always pause. This is one of my fundamental rules. Ask yourself, what type of carbocation is it, and is there anything that we can do to make it a more stable carbocation? In this case, we do have a tertiary carbocation. The positively charged carbon is surrounded by three other carbons. So that's a tertiary carbocation, which is relatively stable when talking about carbocations. But there's going to be a rearrangement here. We're going to steal a methyl group from the adjacent carbon. We'll do an alkyl shift or methyl shift. And when that happens, now this carbon right there on the left becomes a carbocation. Now you might ask, why would that be beneficial? Let's go ahead, show the methyl group. That's the methyl group that migrated over. Here's the other CH3, and now this carbon here is going to be a carbocation. Let me put brackets around that because you can't isolate a carbocation. Ask yourself, this is also a tertiary carbocation. Now, you might think that all tertiary carbocations are created equal. However, if in this case, this tertiary carbocation can resonate, has a resonance contributor where lone pair of electrons from this alcohol, from the oxygen of the alcohol, can come in and stabilize that carbocation. So now we have a double bond to oxygen. This oxygen over here is going to be positively charged. CH3, methyl group. That's the methyl group that migrated over. And we have a positively charged oxygen. Now, oxygen is electronegative and does not like to be positively charged. However, in this case, all the oxygen and the carbons, all the carbons, have an octet of electrons around them. This carbon right here has 4 bonds, so it satisfies the octet rule. This oxygen right here also has 3 bonds and a lone pair, satisfies the octet rule. When drawing resonance structures, molecules that are carbocations are always low on the priority list. As long as all the elements, carbons and oxygens, satisfy the octet rule, that takes precedence. And now the water molecule that came out, that was a leaving group over here, is going to come along and deprotonate this alcohol here, push those electrons back on there, and we've got our final product in which we will have a ketone, carbon-oxygen double bond, and the methyl groups on this rightmost one here, that methyl group was one that migrated over. And so this is the mechanism for a pinnacle rearrangement.